Alright everybody, so let's have a look at this problem here. So you'll note that we have a triangle here, and I've given you three vertices. I've gone ahead and sketched this out here. We want to determine the area of this triangle here. Now, you may recall this, we had a problem very similar to this previously in one of the previous sets. But the easy part about that was that one of the sides was horizontal, so it was very easy to calculate the space and the height. Here, unfortunately, we don't have that. So we're not exactly sure what to do about this here. So there are a couple ways you can tackle this problem, one of which is something known as Heron's formula, which I noticed that some of you used, and indeed, maybe if we have some time later, I'll do something on Heron's formula. But considering this, I mean, we still can do base times height. The problem is trying to calculate the length of a height here, especially since none of the sides are horizontal or vertical here. So the nice part about having a picture like this here is that we have all the vertices. So one thing we can do is we can try to sort of, either we can divide this into smaller pieces in which we can find the area of, or one thing we could do is we can try to, try to build a larger object and just cut away the pieces we don't want. So one thing to note about this here is that note that the triangle only extends horizontally from -1 to 8 here, and vertically extends from -5 to 13 here. So in a way, what we can do is we can sort of encase this entire triangle in a big rectangle here, using the dimensions I talked about earlier. So let me go ahead and do that here. So we note that we create a rectangle here to encase this entire object, and then we can just basically find the area of this rectangle and subtract the area of the three triangles we don't need. So I'm going to go ahead and label the other vertices here. So let's call this here D, E, and F. It shouldn't be too hard to figure out where this is now, especially since we were talking about what was going on. This is going to be 8, 13 here for D. E is going to be 8, -5. F is going to be -1, -5, and now we have all this here. So it makes sense for us to write that the area of triangle ABC is the area of BDEF minus the area of the three triangles, BDF and AEC and CBF, right? So we can just go ahead and sketch that out here. So I'm going to write this one out. Now BDF, as again, it's a rectangle. We saw there's a rectangle here. This has dimensions of 9 by 18 here, so we can go ahead and write that out. It's 9 times 18 minus the area of each of the triangles. So BDF here, in this case, BDF, oh sorry, did I write that wrong? I did write that wrong. I'm sorry. This should be BDA. BDA here, as you can see, in this situation, is going to be 1/2 times 9 times, in this case, 13 minus 6. That's 7 here. AEC here is 1/2 times, the height is 11, and the base is from 5 to 8, which is 3. And then CBF is 1/2 times, in this case, you can see this is 6, and the height here is 18. Okay, so let's go ahead and write this out. So let's see. This is going to be double 81, which is 162, minus 63 over 2, minus 33 over 2, minus, let's see, 1/2 times 6 times 18 is 6, 1/2 of 18 is 9, so that's minus 54 here. So in this case, it's 162 minus 54 minus 63 and 33 together is 96. 96 divided by 2 is 48 here, so we have that. So now we can just put this all together. So let's see. 54 and 48, that is 50, 90, 90 plus 12 is 102, which yields you 50 here, right? So you can see the area of this triangle is 50. Now, note that this should work for any sort of quadrilateral, any sort of figure here. We can sort of encase it into a large rectangle and just chop away the pieces we don't need. Now, some of you may know that there's another way of doing this here, and I'm going to be introducing something here to you known as what is known as the Shoelace Formula, Shoelace Theorem here, okay? So I'd like you to follow along with this here. We're going to be looking at what is known as the Shoelace method. Formula, method, whatever you want to call it here. So the way the Shoelace formula works is like this. So what we're going to do is we're going to list the coordinates of this object here. Now, I'm doing this with a triangle, but you can do this with any object that you choose, any polygon that you'd like here, as long as you know all the coordinates. So the idea here is we're going to list all the coordinates, and we're going to list them in order as we travel around the object here. So now, it really doesn't matter where we start. And it doesn't matter what direction we travel, but we just have to list every coordinate that we hit in that specific order. So for instance, I can go from A to B to C, right? So in this case, I'll list them out. 8, 6, that's A. And then here we go to negative 1, 13. And then here we go down to 5, negative 5. And then remember, and then with this, you want to make sure that with this you go back to the beginning, which means that you want to repeat the first coordinate here. So we have this. So it's 8, 6, negative 1, 13, 5, negative 5, 8, 6 again. So we want these to match here. So this is to create a full loop. Now, this is what we're going to do. We're now going to do some multiplication. We're going to go down and to the right and multiply whenever we see two numbers. So 8 times 13 here, that's 104. Negative 1 times negative 5 is a positive 5. 5 times 6 is 30. Okay. Now we're going to do the same on the left-hand side. So in this case, we're going to go down to the left here. Negative 1 times 6 is minus 6. 13 times 5 is 65. Negative 5 times 8 is minus 40 here. Okay. Now you'll note that in this, when we do this here, you'll note that this kind of looks like bootlaces here, which is why it's called the shoelace theorem, the shoelace formula here. So we're going to go ahead and add, now we're going to add these quantities together. So let's see, we're going to have a red sum here, a blue sum. The red sum is 65 minus 40 is 25 minus 6 is 19. The red sum here is, sorry, the blue sum is 104 plus 5 is 109. That's 139 here. Oh, I'm sorry. I just realized I made an arithmetic mistake over here. 162 minus 102 is 60. I apologize, ladies and gentlemen. So now we can see what's going on here. Now, the idea here is the last thing we're going to do is we're going to take half the difference between these. So it's going to be half the difference between 139 and 139 minus 19. So we take half that difference. It's going to be 1/2 of 120, which is 60, and that matches what we had up there. Now note this shoelace theorem here, the shoelace formula works on any such figure here, ladies and gentlemen. As long as you know all the, as long as it's a polygonal path, and you know the coordinates of every vertex here, this is guaranteed to work. Okay, so again, we're just going to run through it one more time. You want to list the coordinates in order. Doesn't matter which direction you go, whether it's clockwise or counterclockwise, doesn't matter. But make sure you list each vertex in the order that you hit it until you make a full loop. Then multiply down right. That creates a set of sums. Multiply down left. That creates a set of products. Sorry, set of products here, set of products here. And then you're going to create this. Then you're going to add these down, create the sum of these products here, and then find half the difference between. Note that in this case, I took the larger minus the smaller. It may be possible you get a negative quantity. In this case, you just take the absolute value here, so you can guarantee a positive area.